So before the break we concluded that the characters associated with the equivalence classes of continuous finite dimensional representations of a compact Lie group G is an orthonormal system in the space of conjugacy invariant functions, square integral functions on G. And the statement that this is an orthonormal system is really a consequence of the intertwining property and the sure orthogonality relation, all of which we really proved. The completeness of this system, in other words, that it is a complete basis for this Hilbert space, this is basically equivalent to the Peter-Weyl theorem, which we didn't prove in the lectures, but the proof of this theorem can be found in the lecture notes. It requires some functional analysis that would put us too far off track. Okay, let's look at a special case of this situation. Special case that G is compact and abelian, commutative. Well, then we have seen that because of Schur's lemma, the irreducible representations of this group, because of the commutativity, the irreducible representations are all one-dimensional. So, for all irreducible representations of G, we have that the dimension of delta is 1. Well, that means that basically this representation is given by scalar multiplication, right? So the dimension of the representation space V delta is 1, and that means that delta of an X is a linear map from V delta to V delta, but this linear map is scalar multiplication, say multiplication by some psi of X. And what is the trace of this scalar multiplication? The trace of delta of X is of course precisely psi of X. In other words, this psi of X is really the character of delta. So it's multiplication by the character of delta in this case. And so the characters correspond really to characters of the group. Right? So one could now say that this really, by mapping delta to its character, we really get the group homomorphisms, the continuous group homomorphisms from the group G to, say, so G is compact here, so say U1, right? And U1 can be realized as the unit circle in the complex plane, if you like. And this is a bijection. And so, now of course, every function on G is conjugation invariant if G is abelian. So in this special case, we have that, that really these characters give the complete Fourier analysis of the group G. So, for each L2 function on G, we know that F is going to be a Fourier series with summation over these characters or over these irreducible representations, and then we take the L2 inner product with the character to project on that particular subspace, and we multiply with the character. Right? After all, this is an orthonormal basis, and now this decomposition holds in an L2 sense. Now, particular situation of the unit circle. So now we take as our special case the unit circle. So what is the space of characters? So this is, say, complex numbers of length 1. Then it is then the characters are, so the irreducible representations correspond 1, 1 to z. What is the character parameterized by an element n? This is the map e to the I phi element of the unit circle goes to e to the I n phi. The usual Fourier function. Right? And so what does this formula give us? That f of e to the I phi is the same as, well, we take sum over z in an L2 sense, and then we take the inner product with the character. What does it mean? Well, maybe I'll write it out separately. Times the character, which is e to the I n phi. So you recognize the Fourier series here. And of course what we should get here is the Fourier coefficient. Well, let's write out what this means. This is the integral over the circle, and then we take f of z chi n of z bar, and then here we have the measure dz, where this should be the normalized translation invariant measure, but translation on the unit circle is just rotation. So the normalized rotation invariant measure. So if we parameterize the circle by z is e to the I phi, then dz is just the measure corresponding to d phi over 2 pi, the length of the unit circle, in order to get normalized Haar measure. So what we get is that this Fourier coefficient is really the integral from 0 to 2 pi, and then the f of e to the I phi, and then the complex conjugate of this character, which is the complex conjugate of e to the I n phi. Complex conjugate means we should put a minus sign here, and then we have d phi over 2 pi. And this is the classical formula for the Fourier coefficient. So you see that Peter-Weyl can really be viewed as a generalization in an appropriate manner of classical Fourier series. Okay. Now I want to give an application of characters. If we have two representations, pi and rho, two representations, continuous finite dimensional representations of a Lie group G, and suppose that these representations are equivalent, suppose that pi is equivalent to rho. So this means that there is a intertwining operator, so there is a linear isomorphism T from the representation space of pi to the representation space of rho. Linear isomorphism, which is G equivariant. So that means that we have this commutative diagram for all x in the group. T really intertwines the representations rho x and pi x. Well, if we have a commutative diagram of this sort with T a linear isomorphism, then the trace here of this map here is equal to the trace of that map over there. And this is basically because trace is a conjugation invariant. You could also look at it as follows. Take a basis here. T produces a basis there. And of course, because of the commutativity of this diagram, the matrix coefficients of this element with respect to the basis here is the same as the matrix coefficients of the elements here with respect to the image basis over there. So that means that the sum of the diagonal elements are the same. Traces are the same. So what we see is, if two representations are equivalent, then their characters are equal. So pi equivalent to rho implies that the characters are equal. Now the beautiful thing is that sure orthogonality allows us to show that the converse is also true for compact groups. So for compact groups, the character of a representation is a complete invariant of the representation. A representation is completely determined, up to equivalence, by its character. Let's give a proof of that. So let's but for this proof we need a property of characters. So lemma. Suppose that pi and rho are representations, continuous finite dimensional representations of G, then this will give us a representation pi direct sum rho in V pi direct sum V rho in an obvious manner. Right? We discussed this already before, and when we discussed decomposition of representation in terms of invariant subspaces. So basically that means that given an element X of the group G, then the action of this direct sum representation will be pi of X on this component and rho of X on that component. And so what happens to the trace? Well, if you pick a basis here and you pick a basis there, then the two bases together form a basis of the full space. The trace is the sum of all diagonal elements. So first you take the diagonal elements over this space, and then you take the diagonal elements over that space and you add them. So what you see is that the trace of the character of the direct sum of pi and rho is equal to the sum of the characters. Rho, thank you. Now, this has an immediate implication to compact groups, because if we have a compact group and we have a continuous finite dimensional representation, we know it's unitarizable, and therefore it splits as a direct sum of irreducibles. So, let pi be a continuous finite dimensional representation of G a compact group. Then we know that there exists a direct sum decomposition of V pi in irreducible subspaces up to some V capital N. So the VI's are irreducible invariant subspaces. And the representation pi is equivalent to the direct sum from J is 1 to N of the restricted representations. These are irreducible, right? Now, what can we say about the character? So, lemma Let's delta be an irreducible representation of G. Then the inner product of chi pi with chi delta is just the number of j's for which this restricted representation is equivalent to delta. So this is the number of indices j for which the restriction of pi to vj is equivalent to delta. Right, because what we knew is, I'm looking for the sponge. Okay, thank you. So let's give a proof of this lemma. For irreducible representations, we know already. So for so we know that for, so let's write pi sub j is the restricted representation. Pi restricted to Vj. Now we know that there are two possibilities. Either this restriction is equivalent, if this restriction is equivalent, so this is case 1, it's equivalent to delta, well, but then we know that the character of pi j is the character of delta, and that means that the inner product of the two characters is 1, because this is an L2 function with norm 1. Now there is the second possibility is that this irreducible representation is not equivalent to that irreducible representation. Well, what do we know then? Then we know that the space of functions of type pi j is only depending on the class of pi j, and this space is perpendicular to the space of functions of type delta, in particular to the character. Now this contains the character pi j, so by sure orthogonality the characters are perpendicular in the L2 sense. So this is perpendicular to chi delta, the inner product is 0. This is basically the proof. So what we see is that that the inner product of chi pi with chi delta is this character splits as the sum of the characters of the pi j's. So this is the sum from j is 1 to n. And then by linearity of the inner products, we take these inner products. This is 0 when pi j is different from delta, and it's 1 when pi j is equivalent to delta. So this is indeed just the sum of 1 over those indices for which pi j is equivalent to delta. And this is precisely the number of indices for which pi j is equivalent to delta. So we are done. Now, corollary, if we have two representations and their characters are equal, then this implies that the representations are equivalent. Proof, chi pi, though the representation pi has a decomposition into irreducibles, pi 1 up to pi n, into irreducibles. Now this decomposition is now equivalent, this direct sum is equivalent to a direct sum of equivalent representations. So what we can do now is we can take the direct sum over those delta irreducible representations, or equivalent classes of irreducible representations, that is equivalent to well, I should say, so let's so this is a bad way of let's write this as follows. I want to write this, so this, of course, here some of the representations could be mutually equivalent. Collect those together, and then we can say that this is equivalent to, well, take an irreducible representation and take then a number of copies. This number is called M1, and keep doing this. This number is M2 up to the end, delta M plus, well, delta S plus delta S, MS copies, where for all J, for all K and L, if K is different from L, then delta K is not equivalent to delta L. Now we can calculate, so these numbers, the number Mj is called the multiplicity. Well, actually, let's first write down the calculation. Mj can be calculated by taking the inner product of pi with delta j, or of the character of pi with delta j. Take the character of pi and take the character of delta j. Right? This character, the character of pi, splits as the sum of those characters. So maybe let's. Getting a bit disorganized, I'm sorry. Let's get organized in spite of myself. Okay, pi. The character of pi now is equal to M1 times the character of delta 1 plus up to MS times the character of delta S. And now we can say what the j coefficient is. This is just the inner product of chi pi with chi delta j, right? Because all those characters are mutually orthogonal. So by taking the inner product with one of them, I select one of the terms. And then, of course, the multiplicity comes out, and the character has inner product 1 with itself. So now, of course, what I could do is I could write this a bit differently. I could write pi is really equivalent to the direct sum over all equivalence classes of irreducible representations. And now I take multiplicities m delta of pi times delta, where m delta of pi is the equivalence class, is the inner product of chi pi with chi delta. So the meaning of this is, this should be seen as the direct sum of m delta pi copies of delta. And of course this m could be 0. In fact, except for finitely many irreducible representations, it will be 0. And then of course this direct sum should be read as just the direct sum of over those finitely many irreducible representations for which the multiplicity is non-zero. But this is called the multiplicity for obvious reasons. The multiplicity of delta in chi. And what this shows is that the characters give us a way to compute these multiplicities. But this means that if we have two representations that have the same characters, then the multiplicities of all irreducible representations in those representations are the same. So the representations are equivalent. So this basically finishes the proof. Is this clear? This argument? So, sorry?
Should the chi be pi?
In pi, thank you. Yes. So likewise we have that rho is this direct sum. Let's write it out like this, where the multiplicity of delta in rho is the inner product of the character of rho with chi delta. Now if the characters of the two representations are the same, all these inner products are the same, so all multiplicities are the same, so this representation is equivalent to that representation, so pi and rho are equivalent. That's really the proof. Okay.
Capacity is used to first the composition, right?
Sorry?
Where you use the capacity of G?
The compactness. The compactness of G. Right. Yeah, the compactness of G is used for establishing the sure orthogonality relations, because there we need to know that we can take the inner product of characters in the L2 sense. So we need that our integrals converge, and there it's used. Yep. Okay. So note that this proof only uses the orthonormality of the characters. It doesn't use completeness. Right? So we have really given a full proof. Now another important application of this principle is the decomposition of tensor products. And one of the exercises that you saw this morning is about this issue. It should really have come next week. But this is, the problem with this order. It fits naturally here. If we have a tensor product of two representations, what happens to the character? Right. What is suppose that pi and rho are two continuous finite dimensional representations of G. What can we say about the character of the tensor product of the two representations. Lemma. The character is just the product of the characters. The character of the tensor product is the product of the characters. Now this is really, the proof is really straightforward. For instance, by using bases or by interpreting the trace as a contraction, and then see that you taking the contraction of the of a tensor product of two tensor products is really the product of the contractions. That's really straightforward. So this is immediate from the definitions. So I'm not going to give a proof. But now there is a very nice application of this. If we have, for instance, the two representations pi n and pi m, two representations of SU2, then what we can do is we can try to decompose this into irreducibles, meaning decompose it into the pi n's. Now how to do this? Well, compute the character, calculate the inner products of this character with the characters of the irreducibles, and this gives you the multiplicity of the irreducibles in this representation, and then you can write down the decomposition into irreducibles. Right? Okay. So this is a very nice application. I wanted to finish with one more thing today. Let's do that. Let's do that. I promised you that I would prove today that proof lemma that if we look at the group as U2, then we have this collection of irreducible representations, and the claim is that this collection of irreducible representations is now given by the irreducible representations pi n, where n runs over the natural numbers. These were the irreducible representations in the homogeneous polynomials in two variables that we constructed before. And the claim is that these are basically all irreducible representations. Now how should one prove such a thing? Well, what we could do is we could show that so the idea of the proof is that it suffices to show that the characters of these representations follow a form, a complete orthonormal system of the class functions in SU2. Right? So we have, basically these functions are computable. And now we can check whether they form a complete orthonormal system of this space. We can try to check that. If that is true, there is no room for any other finite dimensional irreducible representation. Because if these were not all, then there would be additional elements, additional class functions, which would be perpendicular to the given ones. Right? So this basis could not be complete. So if we can show that this is a complete orthonormal system, then it would follow that really these are all irreducible finite dimensional representations. Now, for this, it suffices to show that if you take the span, so sufficient, show that take the linear span of all those characters, chi n, and show that this is a dense subspace, the linear span is a dense subspace in the space of continuous class functions. Dense in. Equipped with the subnorm. So let's write the subnorm as in this way. If we can prove that, then that means that every function can be approximated with respect to subnorm by finite Fourier series. Yeah. Well, or you could say it differently. What does complete orthonormality mean? It means that if you have a function here in this space which is perpendicular to all these characters, then the function has to be 0. Now, if this is dense in the continuous class functions, then this would mean that if you have a function which is perpendicular to all those, it would be perpendicular to the span of these functions, and then by density it would be perpendicular to all continuous functions, and then you would be able to conclude that the function is 0. So in other words, completeness would follow from density of the span. And now, as you can see in the lecture notes, we can calculate the characters by, basically the characters are completely determined by their restriction on this subgroup T consisting of e to the I phi 0, 0, e to the minus I phi. So this is the subgroup of SU2. The reason is that the characters are conjugation invariant functions, and every element of SU2 is conjugate to a diagonal element of SU2. This is standard linear algebra. So that means that characters are completely determined by their restriction to this torus, and it is quite easy to calculate these restrictions. So what one can show then is that, and then the idea is that class functions are completely determined by their restriction to this subgroup T. Now, so if you look at the continuous functions on this subgroup, then in that space you can see the density, and then you get the density here, and this would give you a proof that in this way you get all irreducible representations. So this is I'm sorry that I do not have more time to elaborate on this argument, but the upshot is that it is the analysis that allows one here to show that one has a complete classification of the irreducible representations. And this is the original approach of Peter-Weyl, by which Peter-Weyl proved a similar result for a compact Lie group. By using the analysis on the compact group, one establishes completeness of a certain set of irreducible representations as basically being representatives of equivalence classes of all irreducible representations. Now, in the rest of this course we are not going to follow this path. Instead we are going to use Lie algebra theory And we are going to use the theory of the Lie algebra to give another proof that these are all irreducible representations of SU2. So I would suggest that you read this proof in the lecture notes. It's completely contained in the lecture notes. See if you understand it. If you don't understand it, please ask me next time. Next time I'll start with the algebraic proof that these are all irreducible representations of SU2. If you're interested in the rest of the story, the relation, so Herman Weyl's ideas about the analysis on compact groups, then you should have a look at the book by Brucker and Tom Dieck, a reference to which can be found on my web page. Okay, let's stop here. See you next week.